Hi everyone, so we're going to cover 10.2.1 today, and that will cover geometric series. So up to this point we have talked about an arithmetic series. If you remember, it's an arithmetic series is taking, so let's just review for a second. An arithmetic series, what we're doing is taking an arithmetic sequence, which would be that list. So let's say I have 2, and then let's say I add 3 repeatedly, so that would be 5, 8, 11, and so on. So the arithmetic series was where we were adding those terms together. So we're going to apply what we know from that and extend it to a geometric series. So we will start by reviewing a geometric sequence. So hopefully you can remember that a geometric sequence would just be a list of numbers that is generated by multiplying each term by the term before it. So that's how a geometric series is generated. You multiply each term by one specific number. And that number that we multiply by is typically called the common ratio. And we use the letter R to denote common ratio because it's a ratio. So for example, again, I'm just talking about a geometric sequence. A geometric sequence, we could do something like this. Excuse me, 3, 6, 12, 24, 48, and so on. So what makes this a geometric sequence? Well, it's a sequence because it's a list of numbers. It's geometric because to get from one term to the next, I'm repeatedly multiplying by 2. So in this case, the common ratio would be 2. So in this first example, we've got this sequence 10, 50, 250, 1250, 62, 30. That is a typo. So that 30 should be a 50. So that should be a 5 right here. There we go. All right, so let's write an equation for this sequence. So we have to think back to how we wrote equations that followed a pattern of repeatedly multiplying. So I'm hoping that you guys will think of our exponential function that we would write as a times b raised to the x. So if you remember here, a was that starting value, and then b is the multiplier, in this case r. A, the starting value, in this case would be the 0th term, or t of 0. So let's apply that to this sequence. So we'll put t of n equals, and then we have a, which would be our 0th term. So you have to think through this one in the same way we did with arithmetic sequences when we had to figure out the 0th term. So if we're taking 10 and multiplying by 5 times 5 times 5 to generate each new term, then to go backwards to the 0th term, I would have to take 10 and divide by 5. So that would mean my 0th term. So if we take 10 and divide by 5, that would mean my 0th term would be 2. So this would have the equation 2 times my multiplier, or b, or the ratio. In this case it would be 5 raised to the n. So then you can just quickly check that. If I plug 1 in here, it should match up with my first term, 10. So 5 to the first is 5 times 2 is 10. 5 squared is 25 times 2 is 50. So that makes sense with our list of numbers. Okay, this next question here, it's asking, is this equation, t of n equals 10 times 5 raised to the n minus 1, is that also a valid way of writing this equation? So let's stop and really focus on the first equation I wrote down. 2 times 5 to the n. We worked backwards to get 2 for the 0th term, and 5 is the multiplier, or common ratio. In this new equation, we start with 10, which is our first term, times 5 raised to the n minus 1. So hopefully this logic you are remembering from similar problems using arithmetic series, but this is also a valid way of writing this. And one of the ways that we can easily confirm that it is the same is just by plugging in a few values. So I'm going to use this equation to figure out if it will still generate our original sequence. So if I plug in 1, then that would be 10 times 5 to the 1 minus 1, which would be 5 to the 0. Well, anything raised to the 0 is just 1, so this simply equals 10, which is our first term, so that lines up. I could try this a couple times just to make sure, or to convince myself. So that would be t of 2 would be 10 times 5 raised to the 2 minus 1, which would just be 5 to the first, which is 10 times 5, which is 50. So this is generating the same sequence. And what it does is it's accounting for this. It's, first of all, I like it because it shows you the first term, and then it accounts for that going backwards that we did up here in this n minus 1. So both of these equations are correct and valid. So we're going to apply that to a new sequence just to get some practice writing the equations. So just to reiterate, up to this point, we have not looked at any geometric series. We've only looked at these sequences, which is just the list of numbers. So we'll jump into series in a minute. All right, so here we've got a new sequence, 54, 162, 486. So how can I figure out what is happening here? So I see the first few terms. To figure out what I'm multiplying 54 by to get 162, you can just go backwards and do 162 divided by 54, and you get 3. Just to make sure this is consistent, I'm going to check the next one and do 486 divided by 162, which is also 3. So you can pretty easily work through and figure out that the common ratio is 3 in this case. So when I start writing out I'm going to do my first one the same way I did the first equation above. So I'm going to go back to my 0th term, and that would mean I would have to do 54 divided by 3, which is 18. So that would be my 0th term, or a. I'm just going to remind you, we are looking at an exponential function. We're just going to write it. Now we're looking at that exponential growth in terms of a sequence. So that would be 18, my 0th term, times my common ratio, which is 3, raised to the n. Or we can write this sequence using this same one we did above, where we looked at that other option of doing it. It's where instead of starting with the 0th term, we can actually start with the first term, 54, times the common ratio of 3, but we need to account for that not going backwards one, and we do that right here, so it's raised to the n minus 1. So these are the two possible formulas you could write, or two possible equations for this sequence. Okay, so let's move on to series. So a geometric series, now that we've reviewed the geometric sequences, the geometric series represents the addition or the sum of all of the terms of a geometric sequence. So make sure you guys are reading and listening carefully based on whether or not I use the word series or sequence. So a geometric series represents the addition or sum, same thing, of the terms of a geometric sequence. So let's figure out if we can come up with a way of finding the sum. All right, so the series we are looking at is generated by this sequence, 2 times 5 to the n minus 1. So this is almost the exact sequence we looked at above, just slightly different. We're going to write out the first 6 terms. So the first term would be generated by plugging 1 in for n right here. So the first term, when I plug 1 into this, it would be 1 minus 1, which leaves us 5 to the 0, which is 1. So that whole thing ends up just being 2 times 1. So our first term is 2. The second term you can generate by plugging 2 in for the n. However, we already know from the equation that to generate each following term, we already know our value of r is 5. So we know that this sequence will continue to grow by multiplying each term by 5. And we were asked to write out the first 6 terms, to write out the series. So I'm just going to underline that because I've already Okay, my eraser isn't working. So I will just have to deal with that little comma, because what I really want to do is write out the series. So that would be 2 plus multiply by 5 and I get 10, plus multiply by 5 and I get 50, plus multiply by 5 and I get 250. So that's 4 terms, and I've got 2 more. So multiply by 5, 1250, and 1 more, 6250. So these are the first 6 terms of my sum, and if you remember the notation from above, I could call this S of 6. So that's the sum of the first 6 terms of this sequence T of n. So this next question is asking, can we use that same rectangular method? So if you remember from the last class, when it referred, or the last video, it refers to Gauss's method of, he did the sum of the first 100 counting numbers. So he did 1 plus 2 plus 99 all the way up to 100, and then he reversed the order of that and he added them together. Whoops. So he added that to itself, but when he added it to itself, he flipped the order. And what he found was that those all added up to 101, 101 plus 101. So it ended up forming this nice, neat rectangle if you had a visual for it. So we're going to see if that works with geometric series, because this was for arithmetic, where you're adding the same number, adding or subtracting. So we'll see if that works up here. So if I flip the order of this sequence, you need a little space, then if I add it to itself, no, I need to, okay. So if I add it to itself, but flip the order, that would be 6250 plus 1250 plus 250 plus 50 plus 10 plus 2. So let's see if, just like we saw down here, each sum added up to the same number. So that's how we were able to represent that as a rectangle, because we could factor out the 101 each time. So if we line these up and add, so if I add 2 plus 6250, so this is going to be 2 S of 6 equals, so that would be 6252 plus, then we're going to add 10 plus 1250, that would be 1260. So already I can see that these sums adding the two series together are not equaling the same value. So it's kind of a red flag. I can continue and I would have this, that would be plus 300, plus another 300, plus 1260 again, plus 6252. So we do see a pattern here. However, these are not all the same numbers, so we can't simply factor out the common factor and multiply it by however many times it appears like we could down here. So the whole purpose of working through that is to point out that the rectangle method does not work on a geometric series. So doesn't work on this. So we're going to flip over and figure out how to do it then, since this strategy with a rectangle doesn't work. So we will work through how to do it together. So let's flip on over. All right. So as we zoom in, okay. So now we're going to figure out how to do it. So this one is not as intuitive as the rectangle method with arithmetic series. So you'll see I've got the process up here, and later we'll summarize this into a formula. You will not need to memorize the formula, but you will need to be able to use it on your own. All right, so let's follow these steps and figure out how to come up with the sum of the first 6 terms of that sequence. So we're going to begin by writing out the series. So we are told to find the sum of the first 6 terms, and so following step 1, we're going to write out the first 6 terms. So that would be S of 6, so that's just the notation for the summation of the first 6 terms. And then again, like we did on the last page, we'll just write those out. So those 6 terms were 2 plus 10 plus 50 plus 250 plus 1250 plus 60, 250. All right, so we've written out the first 6 terms. Go back to our direction box here. Step 2 says to multiply both sides of the series by the multiplier again. So that sounds a little funky, but let's look at our multiplier, or the common ratio, is 5. So what step 2 is saying is take 5 and multiply it by both sides of the equation that we just set up, which means I'm going to multiply this by 5, the S of 6, which means the sum of the first 6 terms, and then each of these by 5 as well. So when I multiply the left-hand side of my equation by 5, I just have 5 times S of 6 equals. Now when I multiply everything by 5 over here, think about what that's going to do. That's going to give me 2 times 5, which is 10, plus 10 times 5, which is 50, plus 50 times 5, which is 250. So again, what I just did is I'm multiplying everything, multiplied 2 by 5 to get 10. 10 times 5 is 50. 50 times 5 is 250. 250 times 5 is 1250, and we'll write all these out. You can kind of think of it as like shifting all these numbers down or up by 1. Plus 6250, and then 6250 times 5 is 31,250. All right, so what does that leave us with? Just to recap, step 1, just write out the sequence itself. Step 2, multiply both sides by the common ratio, or the multiplier. And what you see is it's almost the exact same, but I don't have the first term anymore, and I have this new term out here, which is 5 times my previous term. Now, jumping over to step 3, it says subtract the original series from the one you generated in step 2. So our original series is S of 6. So I'm going to be taking, actually what I'm going to do here is draw a little line. So this, we just listed out the series, and then I'm taking 5 S of 6 and subtracting 1 S of 6. So I'm going to subtract S of 6 from the left-hand side and from the right-hand side. So if I have 5 S of 6 minus 1 S of 6, that would leave me with 4. So 5 minus 1 is 4. So that would give me 4 times the sum of the first 6 terms equals, so when I'm subtracting my original, this is my original sequence, or series, and I'm subtracting that away. So now I'm going to subtract 2 minus 10. So I'm subtracting every single minus 50, minus 250, minus 1250, minus 6250. So again, following these steps, which said subtract the original equation from this middle line here. So I'm subtracting all of the terms away from it. What you'll notice, or hopefully what you're seeing here, is that the 10 minus the 10, 50 minus 50, 250 minus 250, what we see is so many of these terms ending up canceling out when I do this subtraction. And what I'm left with is this very last term here and this negative 2 here. So when I take the 5 S of 6 and subtract 1 S of 6, my result is simply this 31,250 minus 2. So really what we have is 4 times s of 6 equals 31,248. And then I want you to stop and just take a look at what we're seeing. Remember, s of 6 is the sum of the first 6 terms. And that's it. So I know on this one, let me back up. Of course, we could have just typed in each of these 6 numbers and added them up in our calculator. But what we're doing here is trying to find a process for a more complicated or longer series. So we follow these steps in manipulating this equation step by step. And then, but my goal is just figure out s of 6. What is that end sum? So now I'm to the point where I know that 4 of those sums would be 31,248. So then all you have to do is divide both sides of that equation by 4. And then you get the sum of the first 6 terms. So 31,248 divided by 4. And, oops, just divided by 4. And you get 77,812. So what you would do to check that is just add up 2 plus 10 plus 50 plus 250 plus 1250, and you would end up with 77,812. Okay, so now we're in part C. What I'm expecting right now, first of all, I don't want you to feel panicked because this whole thing we just did is a lot to take in. So if you're feeling a little lost, don't worry about it. We're going to go through this process again a couple more times. So the next thing we're going to do in part C is just to find a general equation, meaning instead of saying add up the sum of the first 6 terms, how would you use a formula to add up the sum of the first n terms? So if I could just plug in the number n and get my solution. So we're going to follow the same steps, but instead of the 6 terms, I'm going to write out the series up to the nth term. So the first thing is I just want to reiterate what sequence generates our series, and that's the one I just circled up above. So when I'm writing out the sum of the first n terms, that's just listing out. So 2 plus 10 plus 50 plus all the way up to the nth term. And that would just be 2 times 5 to the n minus 1. So the last term would just be, I would literally just plug in that number n into that formula. So now we're going to follow the next step. Multiply both sides of the series by the multiplier. So when we do that, when we multiply the left-hand side by the multiplier, which is 5, and then when I multiply everything on the right-hand side by 5 as well, what I end up with is 2 times 5, which is 10, plus 10 times 5, which is 50, plus 50 times 5, which is 250, and so on, all the way up to the term right before this one. So remember, the term right before it, let's see. So first of all, these are all just, when you multiply by 5, basically just generating the very next term in line. So when I take this term that's not written here and multiply it by 5, it's going to turn into this one. So that would be plus 2 times 5 to the n minus 1. And then when I multiply my very last term, which is 2 times 5 to the n minus 1, times 5, again, what I end up with is 2 times 5 raised to the n, not the n minus 1, because I will show you in case you're confused. 2 times 5 to the n minus 1, when I multiply that times 5, think about when we take numbers that have exponents, the same base raised to different powers, think about what we do with those 2 powers. Hopefully you're thinking we add. Well, remember, this is really 5 to the first. So when I do 5 to the n minus 1 times 5 to the first, I really just take n minus 1 and add 1 to it. So n minus 1 plus 1 is just n. So that's why this last term is 2 times 5 to the n. Okay, so the next step then is subtract the original series from the one we just generated. So what that means is we're going to take this one we just generated and I'm going to subtract Sn from both sides. So hang with me. We're doing the same steps we did before, just with n instead of 6. Or, yeah. Okay, so then when I subtract Sn, think about what I'm subtracting. So first of all, on the left-hand side, I've got 5Sn minus 1Sn. That leaves me with 4. So this should start to look familiar. And when I do that on the right-hand side, remember I'm subtracting Sn. This is all the terms of Sn. So I'm subtracting each of these terms. So that means I'm subtracting 2, I'm subtracting 10, subtracting 50, all the way up to subtracting this last term, 2 times 5 to the n minus 1. And what does that result in? That results in subtracting off all of these similar terms, these identical terms, 10 minus 10, 50 minus 50. This term minus this term cancel out. The only two terms we are left with are the very first term. Sorry, I'm trying to get a different color. Okay, so I'm left with this -2, and I'm left with this 2 times 5 to the n. So I'm going to actually write them in that order. 2 times 5 to the n minus 2. And then think about how we would solve for s of n. All we would do is divide by 4. So I'm going to summarize that. So this formula for s of n would be, so see how I've got a common term here, 2 here and 2 here. We could factor that out, or we could leave it. I'm actually going to factor it out for the sake of the formula I'm going to give you access to. So if I factor that 2 out, I'm left with 5 raised to the n minus 1. All over 4. Okay. So this formula is what we just generated to calculate the sum of the first n terms of our sequence. And we are going to start sticking with formulas, not necessarily going through this long process that we did here. I just wanted you to see where this formula came from. Okay, so before we move on to example 3, I am going to generalize where each of these numbers came from. So because this formula that I'm kind of pointing to right now, this is what we're going to use moving forward. Now this is just the formula for our sequence that we did, which is generated by 2 times 5 to the n minus 1. So first of all, it needs to be in that form, raised to the n minus 1, and then we can apply this formula. So where did the 2 come from in this context? So 2, in this case, look back up at our original sequence. What is 2? That was the starting term, or the first term in this sequence. So that would be t of 1, sometimes called a of 1. So t1 or a1 is how you'll see it referred to in formulas. 5, where did this 5 came from? Looking back, that's our multiplier, so that's r. This minus 1 is just a part of every formula. And this 4 is 1 less than our multiplier r. So this 4 comes from r minus 1. So if we can, I'm highlighting those patterns because we're going to use this in the next problem. So if we look now to this next example, again, I just want to reiterate, if you're overwhelmed, don't worry. It will get better. You do not have to memorize anything from this. You will have access to this if we do end up, coming back to school and having a test on this. You will have access to the formulas. Okay, so let's look at a new example and see if we can make sense of it. So we've got this sequence. T of n equals 30 times 1.2 raised to the n minus 1. First of all, this is written in that form of a sequence where that 30, because this n minus 1 is here, we know 30 is the first term of the sequence. So this series is 30 plus, the next term, all I have to do is multiply 30 by 1.2, and that is 36. Then I take 36 and multiply by 1.2, and I get 43.2. And so on. So if I go up to the nth term of this series, then my last term would be 30 times 1.2 raised to the n minus 1. So this is the series written out. So what we're going to do now is find the sum of the first 37 terms using the steps from above. So I just changed my mind on, I created this worksheet a while ago, and I'm going to change things up. So I don't want to use the steps from above. We're actually going to rely on a formula. So the first thing we're going to do is actually go down to C and do this one first. We're going to come up with our formula, and then we'll apply it to B to find the sum of the first 37 terms. So to find that formula, we are going to relate it exactly to the formula that we ended up coming up with our last one. So, and it's very straightforward now that we have worked through the rough problem that we just did before. The formula for the nth term, following with the pattern we saw from this last one. 2 here, which was the first term of our sequence in the last one, will actually be t of 1 in our new one, or a1. Again, both of these mean the same thing, which is the first term. So we see from our formula, our first term is 30. So that's going to be the first thing in the numerator. Then we have, up here we had 5 to the n minus 1. Think about 5. In our previous example, that was our common ratio. So we'll just change that to the context of our new example. Our common ratio is 1.2. So it's 30 times 1.2 raised to the n. And then back up here, minus 1. So I'm going to continue that, minus 1 divided by, and then up here where we had 4, that was generated by subtracting 1 from our multiplier. So I'm just going to take 1.2 and subtract 1. In fact, I can just write that out, 1.2 minus 1. So then we can get this simplified formula. So I can find the sum of the first n terms, any number of terms I want. It's 30 times 1.2 to the n minus 1. Oops. Divided by 1.2 minus 1, which is just 0.2. So this formula will help us answer part B. So now that we have this, we can go up and answer S of 37. So let's do that together. So S of 37 is going to be 30. So again, we're just following this. You do not have to memorize how we came up with this. You'll have access to it. So that would be 30 times 1.2 to the n, but in this case we want the sum of the first 37 terms. So here we just plug in 1.2 to the 37 minus 1, all divided by 0.2. So we would just type this in now. When you type this into your calculator, be careful of order of operations. So if you have your calculator right now, you should do 30 first, then type in the parentheses and do 1.2 raised to the 37 minus 1, and then end parentheses, and then divide that number. So I'll show you what I got on my calculator just so you can make sure you got it correct too. 25,486.8675 divided by 0.2. So I'll finish that calculation, and I ended up with a large number, 127,434 about 0.3. So that's the answer. Okay, and again, we can now resort to these formulas, this formula, that for the millionth time you will have access to. You do not need to memorize how to come up with that. Okay, so I just have a few more examples I want to work through on the next page, and then we'll... Okay, so on this page, there are 4 examples here. I'm actually going to skip example A because it would require us to go through the steps, like the long process on A. So I'm actually going to skip to B. First of all, we are asked to determine if each series is arithmetic or geometric, then determine the sum based on what strategies we have. So if we look at B, look at the pattern on the inside. So first of all, we are going back to this summation notation, which again is just the shorthand way of writing out a long list of things added up. So first we need to simplify what's happening on the inside of that summation notation so we can figure out if it's arithmetic or geometric. So we've got 16 minus 4p, or 16 minus 4 times p minus 1. So the first thing we need to do is distribute this negative 4 to both of these, and we end up with 16 minus 4p, and then negative 4 times negative 1 is positive 4. So what we actually have here is the sum of 16 plus 4, so that's 20, minus 4p. And that sum starts at 1 and goes up to 179. So is this arithmetic or geometric? And hopefully you recognize that because to generate each term, you are multiplying by, or actually what you would be doing is subtracting 4 repeatedly. If it helps, we could write it like this. I can't erase for some reason, but if it helps, we could write it like, we could rewrite that as negative 4p plus 20. And then what's happening is you see it look more linear. So that means it's an arithmetic sequence, and thus an arithmetic series. So even though we were focusing on geometric in this one, now we're forced to kind of remember how we did that. And again, we need to think of that rectangle method. So there were 3 pieces of information we used for the rectangle method. If you remember, actually I'll use this space over here. So we had the visual of the bar graph, and then what we did was split that bar graph in 2, rotate the second half on top of the first half. So the 3 pieces of information we needed were the number of terms, and we can see here there's 179. So the sum of the first 179 terms would be, by getting the base of that rectangle now, which would be 179 over 2, times, and then if you remember, we added what was considered the height of this first term plus the height of this last term when they were stacked on top of each other. So that would be the first term plus the last term. So we do need to know what S of 1 is. So we would plug 1 in for P. It would be 20 minus P, or 4 times 1. So the S of 1 is 16. So I'm going to add 16 right there. And then the sum, or the T of 1, sorry. The value of 179 would be, I'm going to write this over here. Plugging in 179 for P. So that would, I'm just going to type that into my calculator. 20 minus 4 times 179, and that's negative 696. Whoops. That may seem weird, but if you look at our formula, 696, we're subtracting 4p. So this number should be getting smaller and smaller and smaller. So it does definitely get into those negatives. So then we would type this whole thing into our calculator and come up with the final sum of 179 terms is 179 divided by 2 times 16 minus 696. And all together that ends up being negative 60,860. So if you did not get that same thing when you type this into your calculator, you might want to go back and try again. So this is just a good review over arithmetic because we have not done arithmetic in this section yet. So that's negative 60, 860. Okay, now we are going to jump down to D. So when we look at D, we want to know, is this arithmetic or geometric? And you can see just from the setup, you've got 4 times 3 to the n minus 1. This looks more like the ones we've been focusing on in this section. So this is definitely geometric because you would generate each term by multiplying by 3. So here we see r is 3. And the first term of the series would be 4. So this would be t of 1 or a1. So we'll see a1 in the formula most of the time. Okay, so if you flip back to the last page, that might help fill in some of the gaps as we write the formula. So we're going to use the formula here. The formula for the first 9 terms. And let's see, I'm even flipping back myself because this is hard to remember all the time. So if we flip back and look at our formula, what we used was, first of all, we had A1, which is the first number. So the first number in ours is 4. So our formula would be 4 times r to the n minus 1. So 3 is our r. Actually, what I'm going to do here is generalize it first. Okay, so this is the formula we're going to apply. A1 times r raised to the n minus 1 divided by the rate itself minus 1. Okay. So this is the formula, again, you will always have access to. So in applying it to this problem, the sum of the first 9 terms, so in this case, n is 9. A1, first term, 4. R to the n, that would be 3 to the n, but we also know that n is 9. Minus 1, all divided by, where happened to my bar? Okay, right there. All divided by r minus 1, which would be 3 minus 1. So we get 4 times 3 to the 9th minus 1. That's going to be a big number. 3 to the 9th, subtract 1. So we get 4 times 19,682. Divided by 3 minus 2, or 1, which is 2. So then if we compute this, we end up with 39,364. So that's the sum of the first 9 terms of this series. So again, this in orange, I should have written that out first. This is the formula you will always have access to. You may see different variations of this formula. So actually, I'm not going to do C with you guys right now. Instead, what I'm going to do is write other variations of S of N. So you may also see, and there's subtle variations, but you may see it depending on the different resources I give you guys to work on here in the next week or two. So some people take this A1 and distribute it to both of those terms. So it would be A1 times R to the N. And then you'll just see it written like that. And then we distribute that to the minus 1 as well. So that just ends up being minus A1 over R minus 1. So this is one variation of this formula you might see. All it's doing is taking that first term A, or in this case 4, and they're just distributing it to both of these terms in the numerator. Another variation you might see is completely reversing the order of the subtraction, which we normally can't do. You can't just say 5 minus 1 is the same as 1 minus 5. It's not. It would actually be the negative of the original. But if you reverse the numerator, you can reverse the denominator, and then it would end up having the exact same meaning. So one other variation of this is reversing this subtraction. So the A1 can still be out, or it could be with it or not. But instead of r to the n minus 1, you might see 1 minus r to the n, which is totally fine as long as in the denominator this subtraction is opposite as well. So that would be 1 minus r. So these are the three variations of this you'll see. And if you see the variations, it's no problem. Just follow along with whatever formula you're given. This is the one I'll probably use in class. Like if we get back to school and we have a quiz or test over this, I'll probably just write this one on the board. So in summary here, we've got two types of series we've looked at. Arithmetic, in which case we use this rectangle method. And then we've got geometric, in which case you will be given access to this seemingly complicated but not too complicated formula. And I say not too complicated because the more you guys practice with this, you'll start feeling better and better about it. Okay, we will stop here and you should be good to go to work through the 10-2-1 homework.